In this video, we're going to solve one practice question on location optimization, question number 10 from chapter 12. And we're going to also see if we can find any alternative optimal solution for that question. We're going to solve question number 11 from chapter 12. So here are the question. Here's the question number 10. So for the CHB bank, they're actually evaluating the potential for expanding their operations into the state of Ohio, which has 88 counties. So similar to the example that we solved before, they're trying to see, the question that they want to answer here is, in which of these counties they have to open a PPB in order to be able to cover the whole region, in order to be able to cover the whole state, all right? There is a data file, CHB, that contains a neighborhood matrix. And in that matrix, whenever you see 1, it means that the counties, let's say here, this means county number 1 and 2 are neighbor, and 0 means county number 1 and 3, they're not neighbors, right? So for example, here, this 1, it means that county number 4 and 3, they share borders. So these 3 and 4, they're neighbors. And for example, 0 here means 4 and 2 are not neighbor, right? So that's how we read these metrics. Now, having that matrix, we want to formulate and solve a linear binary model that will tell this bank company, CHB, the minimum number of PPBs that they require to have in order to be able to cover the whole state, in order to be able to put a branch in every county in Ohio. So let's just talk about the formulation first, and then we go into the data file and solve it. We're going to go to the next sheet and solve the problem. So the decision variables here, like we already talked about that, they want to know in which county to open a principal place of business. For example, if they have a principal place of business in 18, principal place of business or a headquarter, if they have it in, let's say, county 18, it would allow them to not only operate in 18, but also be able to have a branch in all its neighbors, which includes 1, 2, 3, 17, 22 also. I mean, they share a corner point, 21, 20, and 19. So all these neighbor counties plus itself, they can be covered by the company, by this bank, CHB bank, right? So that's what we want to know. In which counties, decision variables, whether or not to establish a PPB or principal place of business in county I. So they have to make this decision 88 times. 88 times. For every single one of them, they need to make this decision, whether or not to establish a PPB in this county, right? That's how we can model this as a binary LP. Whether or not to establish a PPB in county I, and we're going to call this XI. And XI can be either 1 or 0. And 1 means yes, they're going to open a facility, they're going to open a PPB. 0 means no. This is how we can define the decision variables. All right, next, objective function. So in this question, they want to cover the whole state, but their objective is to find the minimum number of PPBs. They want to find the minimum number of PPBs that required in order to be able to put a branch in every county. So their objective is to find the minimum number. So objective function, it's actually they want to minimize the number of PPBs, and the number of PPBs is going to be the sum of the decision variables. So if each decision variable is 0 or 1, and if you add them together for each PPB that you establish in any of these regions, that number is going to go up by 1 unit. So the sum of all these decision variables, x1 plus x2 plus all the way to x88, which is actually the number of counties that we have in state of Ohio, x1 to x88, if all these 88 decision variables, if all of them take 1, meaning that you open a PPB in every single one of these counties, this sum will be 88, right? If you have no facility, if you decide not to open any facility, and all of these xi's take 0, then this sum becomes equal to 0, meaning that you have no PPBs. So objective is to minimize this number, minimize this formula, right? Now, what are the constraints? The only set of constraints that are defined is this. They want to know, they want to be able to cover the whole region. And that means for every single county, they should have a PPB in eligible PPB that can cover that county. So let's say for county number 1, so constraint or coverage constraints subject to the coverage constraints, basic, which means each county should have at least one eligible PPB nearby. So in order to be able to cover each county, there should be at least one PPB nearby. So for county number 1, if you want to be able to cover county number 1, there has to be a PPB either in 1 itself or in one of its neighbors. So I would say if x1 plus x2 plus x18 plus x19 is at least 1, if the sum of these 4, the decision variables for these 4 is at least 1, that means that at least one of these counties, at least in one of these counties, there is one PPB, which means that you can cover county 1. You can have a branch in county 1, right? So county 1, x1 plus x2 plus x18 plus x19. So this is the number of PPBs that can cover county 1. That has to be greater than or equal to 1. County 2. What are the counties that can cover county 2? County 2 itself and all its neighbors. 1, 18, 19 is not there anymore. 1, 18, 17, and 3. All counties that share some border with it. X1 plus X2 plus 18 plus 17. I mean, it's probably better to write them in order. I'm not gonna write it for every single one of them, but X17 plus x18, and that has to be greater than or equal to 1 for county 2 to be eligible to have one branch in it. So 1 plus 2 plus 3 plus 17 plus 18. So all the counties that are in uh, proximity of a neighbor or the neighbors of county 2, including itself. We're going to do it for one more county, number 3. So county number 3 can be covered if you have a PPB in 3, or if you have a PPB in 2, or if you have one in 17 or 4. All the counties that actually share a border with 3, 4, 17, and 2. So x2 plus x3 plus x4 plus x17. All those that actually share a border with 3, 2, 17, 4. That has to be greater than or equal to 1. And then just keep going. You need to do it for 88. If you want to write down all the constraints for this problem, we need to repeat this. We need to be able to capture all of them for 88. But luckily, since we have the data file, we don't really need to spend this much time. We can just use some product function and use the adjacency matrix in order to be able to get the left hand side. Okay, and so let's go ahead. So this is the formulation. There has to be 88 constraints. So let me just add it here. 88 constraints. So there has to be 88 constraints here, and we have the objective function, decision variables. So we're done with the formulation. So let's go ahead and go to the data tab. We have the metrics here. And then we have also, I have also defined the decision variables, all these decision variables. And we have the objective function. The object. So I mean, for each county, we need one blank cell, which would capture the decision variable regarding that county. So 88 of them. All right. And then objective function, as we know here, is going to be the sum of the decision variables. Sum of the decision variables. So you just need to include all the 88 decision variables, sum of all of them, sum of all the decision variables. Now let's talk about the constraint. So for each county, we need to have at least one eligible PPB that can cover that county. So for county 1, we said county 1 itself plus the decision variable for county 1 itself plus the decision variables for all its neighbors. Some of them should be greater than or equal to 1. All right. So we had this right here. So x1 plus x2 plus x18 plus x19 greater than or equal to 1. We can just do that, or if we go up on our matrix here, we see that only 1, 2, and 18 and 19, only these four counties, the on the first row, which actually corresponds to county 1, their neighborhood to county one, their relationship with county one. One means they're its neighbors or itself, and zero means they're not. So instead of adding those, instead of just adding those decision variables in the left hand side, we can use the sum product function. And if you just multiply these row, the corresponding components on this row by the decision variables and add them together, that would do it. That would actually get you this, what you were looking for. So I'm gonna go ahead and write it down. Sum product of my list of decision variables, 88 of them, comma, row one. Row one. B to C, B, CK, B, CK, that's perfect. So I got that. Let me just show you the formula here. Yeah. So this is the formula that I have for the county number one. And that the left-hand side tells you the number of PPPs that cover this region, that are eligible, that make actually county one eligible to have one branch in it, right? That actually make the company eligible to work in county one or to operate in county one. So right now we don't have any PPBs there, so there's nothing right now. If you put one in county one, I'm just gonna try here. If you put one in county one PPB in county one, and one in county two, there are two PPBs that make these county eligible for operation. If you put another one in county three, another PPB in county three, it's not gonna affect this number, right? It's not going to affect because county three is not its neighbor. So I'm just trying to show you how this function works. So let me just get rid of all these numbers. So we need to just do exactly the same thing for 88 counties. So I'm gonna copy my formula, but before that I need to fix something in my formula. I need to first fix the decision variables, because for county two is going to be the decision variables multiplied by the second row. So I want the rows to be adjusted each time, but the decision variables, I want them to be locked. I want them to be fixed. And let's now drag it down. Let's just take a look. 88. Let's take a look for county 88. Let's see if it's working properly. The row for county 88 multiplied by the decision variables. So that's perfect. And I want every single one of them to be greater than or equal to 1. All right. I'm not going to write it or I'm not going to copy the formula because in our solver, we can just type 1. That's what we want to do. So everything is ready. We have the decision variables, objective function, and the constraints. The left-hand sides and the right-hand sides for all of them is going to be 1. So let's go ahead, go to the solver. We want to find the minimum number of counties, minimum number of PPBs by changing B96 to CK96. All right, or you can just select it by clicking on those. And subject to the constraints, we have 88 constraints. All the left-hand sides, I want them to be greater than or equal to 1. Let's take a look. Minimization of B98, the minimum number of PPBs, by having 88 decision variables subject to 88 constraints. There's one last thing. I need to make sure that all my decision variables, all of these guys, are binary, are defined as binary variables. So I'm going to add again the decision variables. CK96, yes. I want all of them to be binary. Okay, that's perfect. Make sure the solving method is set to be simplex LP and go ahead and solve it. Solver found a solution, a feasible, optimal solution, and all the constraints are satisfied. So that makes it a feasible solution. All optimality conditions are satisfied. That will make it an optimal solution. Okay. So the best as the solution, the minimum number of PPBs that makes the banks, CHP bank, eligible to operate in the whole region, in every single county, is 15. So you have to have at least 15 PPBs in the county, in the Ohio state, in order to be able to operate in the whole state, in order to be able to operate in every single county in the state. All right. So that's the answer to part to question number 10. So it asks, formulate and solve a linear binary model that will tell CHP the minimum number. So we just did question number 10. Let's just now jump to question number 11. For problem 10, use equation 12.1 to determine whether your solution to problem 10 is unique. Basically, we're trying to see if we can find an alternative solution as a best answer, an alternative best answer, or a second best answer. And it asks how many optimal solutions, different optimal solutions are there. So we just found one of them. All right. Now we're trying to see if we can find an alternative solution. Let's just do that. I mean, depending on how long it's going to take, I may do one or all of those. We can continue up to 3 times, but let's just copy this. Okay. Alternative search constraints. So for when we're working with binary optimization, there is a trick for finding the alternative optimal solutions, and it's actually guaranteed to work for sure, 100%. It's going to give you an alternative optimal solution if there's any, or it's going to give you the second best answer if all your decision variables are binary, which is the case for our problem. So it's guaranteed. Adding the alternative search constraint, it's going to give us, it's going to definitely give us an alternative solution if it exists. So for alternative optimal solution, the way we do it when we have binary constraints is when you do this ones minus, or sum of ones minus sum of zeros less than or equal to number of ones minus 1. Let me just change it to sum of ones, sum of zeros less than or equal to the number of ones minus 1. Number of ones we already know in this set of decision variables. Out of 88 decision variables that we have, 15 of them are ones. So you can just, we have the sum of those, right? So the sum is 18. So the number of ones in my set of 88 variables is 15. So now I just need to write down the constraints and add it to our solver. So let's first write it down. So the left-hand side is going to be sum of all those variables that took one. And it's, since we have 88 of them, it's going to be tricky. It's going to be time consuming. So comma, you need to capture all the ones. It's going to be a little slow, but we will get there. After each one is picked, I'm adding a comma in order to separate them and in order to fix them in my formula. AZ96, this one. BD96. BH96 and BQ96. BX96, CA96, and CJ96. So these are all ones. So sum of ones minus sum of zeros. So I'm going to go back from the beginning and start again. Minus sum of all the zeros. Come on. Come on. These two. Come on. So sum of all the zeros. So that would give us the left-hand side, and that has to be less than or equal to 15 minus 1, 14. All right. So we just need to add this to our solver, but you can always make sure to record your original optimal solution just in case, because it's going to change, right? So let's go ahead and add this to the solver. So solver, add the left-hand side less than or equal to 14, number 14. Or you can type 14 or you can add it. You can type it here and then refer it here. Okay. And let's go ahead and solve. If the objective function stays the same, it means that we have found an alternative optimal solution. If it becomes worse, it means that we have found the second best alternative, a second best solution. Okay, so solve, of course, it found a solution. And the good news is that it's the objective function is still 15, and the new constraint is satisfied, 13. It was 15, so the solution is definitely different with the previous one, but the objective function is 15 is the same. So I'm going to copy the new solution that we found and paste it right here. And you can compare these two solutions. You see, before we had one at 18 and nothing in 19. Now we have one. We don't have anything in 18 and we have one at 19. And I'm sure there can be other differences. No, they're exactly the same. The only difference was at 18 and 19, right? So 18 and 19, actually, we had a shift of PPBs. So that's for alternative number one. So if you want to keep doing this and see how many alternative optimal solutions you have, you need to keep adding constraints. I'm going to do one more time. I'm going to do this process one more time, but you can just keep doing it until you find all the alternative solutions. But the only thing that you have to be careful is that when you write down the new constraint, you need to add it to the solver, but you have to still keep the previous one because that one will make sure that you don't get the original optimal solution. So you keep that one and then add the new constraint. So the new constraint is going to be, I'm just going to write it down once. So it's going to be sum of ones, 14, 17, 19. You know what? It was actually exactly the same as previous one. It was the same as the previous one, except for 19 and 18 that we changed them. So I'm going to exactly copy the same formula, Control C, paste it right here. I said 18 and 19. Let's take a look at them. S and T. All right, so I'm just going to change those. So S and T, S here, or ST. I had 17 and 18 before. RS, let's just change it to this. So S is not anymore. S is not 1 anymore, but T is 1. So I change this to T. And here, instead of T, here now, I need to add T and exclude S. I need to add S96 and exclude TRSTU. So I added S to my zeros and I excluded T's. So I started here. Instead of T, I started from U. So that's all good. So now it's 15 and I want it to be less than or equal to 14. I just type 14 again because it's number of ones, which is 15 right here, minus 1, 14. So I just need to add this new constraints to my solver, and I'm going to keep my previous one. I just add the new one, 14, or you just refer it to 14. Okay. And then solve it again. We found the same, we found a different answer. So you see it's different. You see both of these constraints are satisfied now. We found a different answer with the same objective function. So that's my, actually the second alternative or the third optimal solution, and see what changed. So we have 4 here, 4 is added, and 18 is now there. 18 is there, but 19 is not. So it's, and then 17 is not, right? So 4 is added, 17 is dropped. And the rest, I believe, should be the same. Yeah. So that's the third alternative solution. You just keep doing this. So it's similar to, you need to add again another one here, add 4 to 1s and drop 17 from zeros. No, add 4 to 1s and drop it from zeros. Add 17, drop 17 from 1s, add it to zeros, and then less than or equal to 14, and do it, and keep doing this until you get a solution with an objective function more than 15. Probably 16 is going to be your best alternative, your second best solution. So you should expect to have, I think, one or two more optimal alternative optimal solutions.